Hello students, welcome back to my channel. I am Dr. Hina Sheikh back with you again to teach you some more basics of chemistry. Today we are learning everything about titrations. You must have seen the video where I have discussed with you the common Viva questions which are asked on titrations, but everything could not be covered there because it's a huge topic. So I'm covering very important aspects about titration which you must know before you go for the practical exam or before you actually perform the practical in the laboratory. So what we are going to learn are the four type of titrations: direct and indirect titrations, what are iodometric and what is iodimetric titration, what is titrant and titrand. At the end of the video, I'm going to share with you a very favorite question of the examiner. So stay tuned and watch till the end. We move on to the next slide. First, let us understand what is titrant and what is titrand. Titrant is the reagent of known concentration which is filled in the burette. Titrand is a substance being titrated which is generally taking the conical. So you can see the picture on the slide. You can see a burette. In that some solution is there. A conical flask is there. In that again some solution is there. So you have already done titration, so you know that there is a burette solution and there is a solution in the conical flask. What you have to remember is titrant is a solution in the burette and titrand is the solution in the conical flask. Okay. And now how will you remember this? Remember titrant T, it is at the top. Okay. And titrand, the word is D, it is down. So now you can remember titrant is top and titrand is down. So titrant is the solution which is taken in the burette and titrand is the solution which is taken in the conical flask. Another thing to remember is you can be asked that which solution is taken in the burette, known concentration or unknown concentration. So you should know titrant is known or unknown, or titrant is known or unknown. So the answer to this is titrant. Titrant is always a known solution. Titrant is always a known solution or a primary standard. Titrand is an unknown solution or the solution whose concentration you want to find. So I hope you have understood the difference between titrant and titrand. So I move on to the next slide. Let us now understand four types of titrations. The first type of titration is acid-base. So the examiner will ask you what are the four types of titrations. Your answer would be acid-base, redox, complexometric and precipitation. Let us see each one of this. Now I'm not going to go into too much details of this type of titrations because that is going to take hours. I just want to brush up the basics, and that's why I've just taken the cream of these topics. I have not gone into the cake. I've just taken the upper cream and I've presented in front of you. So let us understand what is acid-base titration. Acid-base titration is also called as neutralization reaction. Acid is titrated against a base or vice versa. So whenever in the burette or in the conical flask you have acid or a base, so your titrant would be an acid or a base, or titrand would be an acid or a base. That time it is called as an acid-base reaction. Means in short, you are reacting an acid with a base. The indicators which are used in acid-base titration are phenolphthalein, methyl orange, methyl red. Phenolphthalein is the indicator which is used most number of times. So majority of the acid-base titrations are done with the help of phenolphthalein. Not necessary, obviously we use methyl orange also, we use methyl red also. But how do you remember when we use phenolphthalein? We use phenolphthalein mostly when NaOH is there in the solution. Okay, so NaOH has a relation with phenolphthalein. So remember, whenever NaOH is there, you use phenolphthalein as the indicator. Now which indicator to use in which type of titration? This also is a big theory which I may explain you sometime else, but for the time's sake, just remember there are three indicators, three commonly used indicators in acid-base titration, which are phenolphthalein, methyl orange, and methyl red. I move on to the next slide. Next type of titration, the second type is redox titration. Redox titration takes place when oxidizing agent is titrated against a reducing agent. So your titrant would be a reducing agent or an oxidizing agent, and your titrand would be again a reducing agent or an oxidizing agent. So whenever these two, oxidizing agent and reducing agent, they react, it is called as a redox titration. Obviously in this type of titration a redox reaction takes place. What is a redox reaction? Simultaneous oxidation and reduction. So electrons are transferred from one species to other. The example of redox titration is potassium permanganate titrated against oxalic acid. The indicator used in this first type of titration is self-indicator. Remember, potassium permanganate is a self-indicator. It changes color in acidic medium and basic medium, so you don't need an external indicator. Potassium permanganate is called as an self-indicator. The second example is potassium dichromate. You titrate using diphenylamine as the indicator. So diphenylamine is an example of redox indicator. And why can you use potassium dichromate? Because chromium exists in two different oxidation states, and in these two different oxidation states the color of uh, the color of potassium dichromate will vary, or the color of diphenylamine indicator would vary in oxidized state and reduced state. Mostly it's not about the reagent showing you two colors, it is the indicator showing you two colors in oxidized and reduced state, and that's why it is called as indicator, because it has two different colors in two different states, and that's why you can find out where the endpoint has reached. So I move on to the next slide, which is complexometric titration. In complexometric titration, always EDTA is used. Okay, so whenever you are using EDTA, you remember that it is a complexometric titration. It is called as complexometric because there is a formation of complex. This reaction is used to determine the concentration of metal ions in the solution. You can see here in the burette we take EDTA. Here we use metal, the solution whose concentration has to be found, the metal ion, and along with it we add the indicator. This indicator is called as metallochromic indicator. So what happens? Initially what you have in the conical flask, you have metal and you have indicator. So metal indicator complex is there. To this you are adding EDTA from the burette. So when do you add EDTA? Remember, EDTA is a very good complexing agent. It forms complex with almost all the metal ions. So when you add EDTA, EDTA is going to replace the indicator. So after the reaction, metal is forming complex with EDTA and the indicator is set free. Okay, the color, final color is the free form of the indicator. Your end point is the free form of the indicator. Another thing you have to remember, the full form of EDTA. Full form of EDTA is ethylene diamine tetraacetic acid. This acetic acid salt is very difficult to dissolve in water, so you take warm water, and also we do not use acetic acid form, we use sodium salt of this. So EDTA powder which you are using in the lab is the sodium salt of ethylene diamine tetraacetate ion. Okay. Also, whenever you use EDTA, you are supposed to use distilled water. Another question which you can be asked by the examiner is, why do you use distilled water when you are titrating EDTA? This is because, as I told you, EDTA is a very good complexing agent. So if your tap water contains any metal ion, EDTA will form complex with that also. So to avoid that, we use distilled water which do not contain any metal ions, do not contain any impurities. So I hope complexometric titrations are clear. I now move on to the fourth type of titration, which is precipitation titration. Precipitation titration is a type of titration which involves formation of a precipitate during the titration technique. So In this, you remember the titrant reacts with the titrand to give you a precipitate. Obviously, it is insoluble precipitate, otherwise it would have dissolved. So as you can see here in the picture, these solutions are turbid. Why the solutions are turbid? Because there is a formation of a precipitate. This solution is clear, and here there is formation of precipitate, indicating that your reaction has started. So indicators are there which will indicate that the reaction has taken place. The example for this precipitation titration is Volhard method, Fagen's method, and Moore's method. For details, you can refer to the books which I am writing in the description box. I can suggest Volhard, um, or you can refer to Skoog for further details. Next, we are going to learn what is the difference between iodometric and iodimetric titration. You have done titrations of iodometric and iodimetric, but you do not know the difference. So now I'll explain you the difference between iodometric and iodimetric titration. Let us first see iodometry. In iodometry, iodide reacts with another oxidizing agent in an acidic medium or neutral medium. When this reaction takes place, we add iodide in the form of Ki, oxidizes to iodine, and other species will undergo reduction by iodide. Then we can titrate the released iodine with another species. This titrating species is a standard solution of a reducing agent which is capable of reducing iodine back to iodide form. Usually we use a standard thiosulfate solution for this. So I know you have not understood. I'll explain you, don't worry. So whenever you do any experiment where you add Ki, okay, suppose some species you have to find out. In this example, you are finding out chloride ions. So to the chloride ion solution, we add Ki. So chloride will react with Ki to give you iodine. I2 gets liberated. We say iodine is liberated. We produce iodine in the reaction mixture. Okay, this liberated iodine we capture using starch. Okay, so the starch iodine complex is then broken by sodium thiosulfate, which is taken in the burette. So when you react sodium thiosulfate with I2, you get this, and I minus comes back. So initially you started your experiment with Ki, adding Ki. In Ki, iodide is there, I minus. So this I minus gives you I2, which is liberated. The liberated iodine again reacts with sodium thiosulfate to give you I minus. So remember, I2 gets converted to I minus iodide, and iodide gets converted back to I2. I repeat what I said. First we start with iodide I minus. I minus gets converted to I2. I2 will liberate. Iodine is liberated, correct? So this liberated iodine is titrated against sodium thiosulfate, and we get back our I minus. So for this, we titrate the mixture with the standard sodium thiosulfate solution. We need starch indicator to determine the endpoint of the reaction. With iodine and starch in the mixture, it will appear dark blue in color, but at the end, when all iodine is finished, dark color will disappear. Another thing you have to remember while doing this type of titrations is, do not add starch in the beginning. Always starch is added towards the end point. Now there is a reason for this. What is the reason? Because starch is forming complex with iodine. Okay, when initially you add starch, the iodine concentration is very high. So to this high concentration of iodine, when you add starch, it forms complex which does not break. You get flakes in the solution, flakes or particles, black colored particles. Okay, so when you get flakes, you get black colored particles. On adding starch, you remember that to the excess concentration of iodine you have added starch. That's why this has taken place, which is wrong. But don't worry, whenever this happens, you shake your conical flask properly so that that complex dissolves. Keep on titrating it with sodium thiosulfate and keep on shaking it vigorously so that those particles dissolve. And because of this reason, we do not add starch in the beginning, we add it towards the end point. So initially the color, when iodine is liberated, the color of the solution is dark brown. When it becomes yellow on titration with sodium thiosulfate, when it becomes yellow, you add starch. On adding starch, the color of the solution becomes violet. To this violet solution, you continue the titration till you get a colorless solution. You'll not get colorless solution, you'll get a white colored milk-like solution. Okay. So I hope you have understood iodometric titration. Now let us go on to iodimetric titration. Now in iodimetry, we uses free iodine to undergo titration with a reducing agent. Therefore, iodine reduces to iodide and iodine will oxidize other species. Since we cannot easily prepare a free iodine solution, we have to mix iodine with potassium iodide and Ki3 solution to prepare the required solution. And a standard solution of this is used for the iodometric titration. So Ki plus I2 gives Ki3 and I2 plus the reducing agent gives you 2I minus. So I know you have not understood this. Just listen to me. What is iodimetric titration? In iodimetric titration, you take I2 in the burette. That's it. Okay, what to remember? In iodimetric titration, I have shown this burette with a violet color just to make you remember that I2 is taken in the burette. So when directly I2 is taken in the burette, it is called as iodimetric titration. And when you liberate iodine in the reaction and then you titrate, it is called as iodometric titration. Okay, so how to remember iodometric titration? Iodometric titration is where you produce I2. You produce I2 in the solution. And iodimetric titration is where, see, this is I. So remember I2. Okay. I2 is there in the burette. Okay. I is already there. Correct. I means iodine is already there in the burette. Here I is not there. Here I is not there. What does it mean? It means you're going to produce it. It's not there. Remember this 0. What does this 0 means? It is not there. I2 is not there, which you are going to produce. You produce it by adding Ki. Okay, I hope you will remember this. Let us now see the difference between iodometric and iodimetric titration. Unlike iodometry, it is an indirect titration method. Okay, why is it indirect titration method? Because you are first producing I2 and then you are titrating the liberated iodine with sodium thiosulfate. This is a direct method where directly you are using I2 in the burette. Here the total number of redox reactions is 2. Why 2? Because in the first step you produce iodine, in the second step you react iodine with sodium thiosulfate, so 2 steps. Here only 1 step. Iodine is titrated against whatever is the analyte. Here initially iodine will get oxidized and then get reduced by the reducing agent. Here iodine will get reduced. So I2 is there in the burette and it's going to get reduced. It is used to quantify oxidizing agents. Okay, so here you find out the amount of oxidizing agents. Your analyte is the oxidizing agent. Here in iodimetric titration, it is used to quantify reducing agents. Remember, reducing agent you quantify or you find out how much is the amount by using iodimetric titration. The next topic you have to remember is direct titration and indirect titration. Again, very favorite question of the examiner. You cannot afford to miss it. Okay. So let us see what is direct titration, what is indirect titration. Direct titration is the basic titration method which involves reaction between the unknown compound and the known compound. So whatever titrations you are doing, one step titration, are all direct titrations. Okay, all one step titrations are direct titrations. Now what are indirect titrations? Indirect titrations are also called as back titration. Now I'll just read out for you and then I'll explain you. A back titration is a titration method used to determine the concentration of an unknown using an excess amount of a compound with a known concentration. There is a chemical reaction between these compounds. Since the amount of the compound with a known concentration is added is already known already, we can determine the amount of compound that has reacted with the unknown compound by doing back titration. Okay, so I'll explain you what is this. Let us consider an example in order to understand this concept. We are given a metal ion solution. So I'll explain you this. What happens in back titration? In back titration or indirect titration, just like direct titration, you cannot react A with B. Titrant with titrand do not react. They do not react directly. Okay, in direct titration, you add A to B, titrate, endpoint, khatam. Right? But in indirect titration, the A and B are not going to react directly. So what do? A is there in the burette, B is there in the conical flask. So you add to B, you are going to add excess amount of C, known excess amount of C. So what will happen? Some amount of C will get reacted with B and some amount of C will remain behind. Correct? So whatever amount of C is remaining behind, that is going to react with A. So you do the titration, you add excess amount and you do the titration, so you will get the amount of C which is remaining behind. Okay, this is one. Second part is you do one more titration where you take that excess amount, how much ever you have taken, that you take directly in the conical flask and you do the titration. So you'll get the total amount. In first part, what you have got? The amount left. So total amount minus the amount left will give you the amount of C which has reacted with B. So how much would be that amount? How much of B would be there? That much it would have reacted with C. So that is going to give you the amount of B in the solution. Let us take an example and understand this. A metal ion with an unknown, a metal ion solution with an unknown metal ion concentration is taken. To this, we add EDTA, a common titration method for the analysis of this solution. So what do? We add excess amount of EDTA to the sample solution. The concentration of EDTA should be determined later using a primary standard. So you find out what is the total concentration of EDTA, what is the reading for EDTA for the total amount. Then to the metal ion solution you add that much amount of EDTA. So what will happen? Metal will react with EDTA and some amount of EDTA would be left behind unreacted because you have added excess. The addition of EDTA will cause the formation of metal EDTA complex, okay, in the conical flask. Then the remaining amount of EDTA present in the sample is determined using Mg solution. So Mg is taken, magnesium is taken in the burette and you do the titration using Erichrome black tea indicator. Okay, so two metal ions are used here. One is unknown and second is known. Metal ions always form complexes with EDTA in 1:1 ratio. Since the previously added amount of EDTA is known, we can calculate the amount of EDTA that has reacted with the unknown metal. So I hope you have understood what is direct titration and what is indirect titration. Direct titration is where you are just reacting A with B. That's it. In direct titration, there are two steps. In the first step, what you do? You find out the total concentration of the reagent you are going to add in excess. Okay, so that first you do the titration, you find out the total amount. Then what you do? To your unknown solution, you add that much amount of your solution. So what happens when you add that? Some amount will react with the solution, some amount will be left behind. So whatever is left behind is then titrated. So you get the amount which is unreacted. So total amount minus the unreacted amount gives you the reacted amount, correct? And how much will it react? How much is your unknown present? That much it will react. So I hope you have understood direct titration and back titration. Let us see here the difference. A back titration is a titration method used to determine the concentration of an unknown solution using an excess amount of a compound with a known concentration. Okay, a direct titration is the basic method where you just titrate a known with a unknown. Here two steps are involved. This is back titration. I've taught you first direct then back. So here it is written in the opposite way. This is the one which is direct titration and this is back titration, so don't get confused. In direct titration there is one step, one chemical reaction. In back titration there are two steps, two chemical reactions which occur. The titration is done between a known and unknown compound, correct? Always we do this, we titrate always a known with the unknown. The titration is done between two known compounds. Okay, so two known compounds are taken here. Here the titrand is the unknown compound. Here the titrand is the remaining amount of the reagent which is added in excess. Used when endpoint can be easily obtained. Okay, here the endpoint can be easily obtained. You just take known and unknown, titrate them, get the answer. This you do when you do not get a sharp endpoint, and that's why you have to do a indirect method. So I hope now you have understood the difference between back titration and direct titration. If you have still not understood, you can ask me in the comment box. I'll explain you again. I now come on to a very important point. In titration, you cannot do titration without understanding this. And if you have already done, it means you have done it without basic knowledge. You have just taken burette, pipette and done the titration. You do not have basics. If you do not understand this, means you have zero basics. So let us start with the difference, understanding the difference between the equivalence point and endpoint. Majority of the students feel that both are same, but both are not same. The point in the reaction process where chemical reaction in the titration mixture ends is the equivalence point. So where your reaction is actually ending is the equivalence point. The point in the titration process which is indicated by a color change is called as an end point. So where you can see the color change is the end point. So to understand this, let me explain you this properly. See, suppose you have in the burette, suppose here you have in the burette NaOH, okay, and in the conical flask you have HCl plus the indicator. Can you tell me what would be the color of this initially? Initially the color would be colorless because phenolphthalein is taken here. Phenolphthalein in acidic medium shows you no color. It is colorless in acidic medium. After the endpoint is going to give you pink color. Okay, so what is the color of phenolphthalein in acidic medium? Phenolphthalein is colorless. In basic medium, phenolphthalein is pink in color. Okay, this you have to remember. So initially this is colorless, phenolphthalein is colorless, acid is there. From the burette, suppose how much HCl I have taken? 10 ml. Okay, 10 ml HCl is there, 0.1 normal 10 ml HCl, and here also I have 0.1 normal NaOH. So when I go on adding NaOH from the burette, HCl will go on getting neutralized. Drop by drop I add NaOH and drop by drop HCl will get neutralized. A point will reach where all NaOH will react with all HCl. So all HCl from the solution is being consumed, okay, and that point the solution pH is 7. Okay, I told you in acidic medium indicator shows you no color, it's colorless, and in basic medium it shows you pink color. So what about neutral point? At neutral point again it is colorless. Okay, so the end point has reached but you cannot see. Fine. This is called as the equivalence point. Equivalence point is the point at which your titrant has reacted completely with the titrand. Okay, but you cannot see the color change because still the indicator has not shown you the color change. So one more drop of NaOH, the solution will turn pink and you will be able to find out the end point. That point is called as end point because there you can see the color change. Phenolphthalein is going to show you color change. The solution is going to turn basic. So phenolphthalein will become pink, and you will come to know that endpoint has reached. You note down this and you write down this in your books. This is called as the endpoint, where you can see the color change. Okay. Equivalence point is where the reaction has occurred, completed. Okay, but you cannot see the color change because indicator has not indicated you. Indicator has not shown the color change. Okay, I hope this is understood. I now move on to the favorite question. I told you in the beginning, wait for the end. A favorite question of the examiners, even my favorite question. Whenever I take Viva, I also prefer this question. So this is the favorite question of the examiners, including me, which I'm going to teach you now. This is primary standard and secondary standard. Majority of the students do not know still what is primary standard and what is secondary standard. So let us quickly understand what is primary and what is secondary standard. Primary standard is a substance of known concentration. Okay, primary standard is substance of known concentration, or you can find out its exact concentration. If you remember in the lab, you weigh some compound. Okay, on the balance you weigh, some amount is given to you, that much amount you weigh, you transfer it to the either to the beaker or to the conical flask, and you add minimum amount of water, right? You are told by the teacher to dissolve it in minimum amount of water, and then you dilute it up to the mark using distilled water, and this is how you prepare a standard solution. So you have all set of calculations. How do you prepare standard solution? So I will teach you that some other time. How do you prepare standard solution? How that amount value comes 55.5 grams, okay, or 0.55 grams, 0.49 grams. Some amount is given to you. So how to calculate that I'll teach you some other time. But just remember, the procedure is to prepare a standard solution and you prepare the exact concentration. The concentration remains constant with time. So suppose today I have prepared zero point 0.1 normal succinic acid. After 10 days the concentration will remain the same. After 20 days concentration will remain the same. Maybe after 6 months also concentration will remain the same, unless my solution evaporates. Concentration remains the same with time, does not change. Okay, it is mostly the titrant. You already know what is titrant. It is a solution taken in the burette. So the examples are succinic acid, K2Cr2O7, potassium dichromate are the examples of primary standard. What is primary standard? Primary standard is the solution whose concentration is known. Okay. What is secondary standard? Secondary standard is solution whose concentration don't know. You have to find out. Okay, so all solution, all the compounds which do not come in primary comes in secondary. So all compounds are called as secondary standards whose concentration you have to find out. You don't know. Okay, is a solution of unknown concentration. Its concentration is found using a primary standard. So a primary standard would be there in the burette, and secondary standard you take in the conical flask. This is mostly the titrand. Okay, the example of this is NaOH. Now why does NaOH a secondary standard? Because if you see here photo of NaOH, NaOH is hygroscopic, it absorbs water. Okay, so when you weigh the amount, you do not get the exact amount. You weigh water molecules also along with it. Okay, that's why you cannot prepare exact concentration of NaOH. So you prepare some concentration, whatever is there, you prepare, and then you titrate with the primary standard and find out its exact concentration. This procedure is called as standardization. What is standardization? Standardization is a process where you find out the concentration of a secondary standard. There are few requirements of a primary standard. It must be prepared easily and purified. It must be stable and easily stored. Where it is weighed in open air, it must not react with any component of the air. It must be non-hygroscopic, means it should not absorb water molecules. it should provide accurate result. Okay, the example is succinic acid and potassium dichromate. Many other examples are there. You can refer your books. So this is all I had from my side. I hope all the basics of titration is now understood. If you still have any doubts, you can rewind the video and see it again, which is not possible in normal class. You cannot rewind the teacher, but you can rewind the video anytime. So go back, watch it a number of times till the things fit into your brains. Thank you so much for watching. Do like, share and subscribe. Share it with your friends. Thank you so much.